Hello students, welcome to EduWave online classes. Today we are going to learn conservation of energy. This is the last part from the chapter of work power energy. The first three parts have already been uploaded. So kindly subscribe our YouTube channel and follow us on WhatsApp to stay tuned. Let's start. According to law of conservation of energy, energy can neither be created nor be destroyed. That means whatever energy is present, it is present in the nature. Okay? We can only transform energy from one form to another. Like energy can be transferred from chemical to heat, light and sound. Energy can be transferred from electrical to mechanical or vice versa. Like this, there are different transformations of energy. Now, one thing we have to remember that for mechanical energy, law of conservation of mechanical energy states that the sum of potential energy and kinetic energy is equal to constant, provided there is no dissipation of energy in the surrounding. So if potential increase, energy increase, kinetic energy has to decrease in order to keep this sum constant, and if kinetic energy increase, then potential energy has to decrease in order to keep this sum constant. So here we will be considering two cases. One is law of conservation of mechanical energy for a free falling body and a simple pendulum. So let's see. So, first case we are considering for a free falling body. Okay. So here we are considering this is the ground. Now let's draw this ground a little lower so that we get enough space. This is the midpoint somewhere in between, and this is the ground. Okay. Now the body initially is kept at a height h above the ground. The body is kept at a height h above the ground. So at the topmost point, gravitational potential energy is equal to mgh, right? At the topmost point, gravitational potential energy is mgh, and since the body is at rest, so kinetic energy of the body over here is equal to 0. That means the sum of potential energy and kinetic energy, that means the overall mechanical energy at the highest point, mechanical energy is equal to mgh plus 0, that is mgh. Now we will consider this point. Let us consider this point as A, this point somewhere in between as B, and when it touches the ground, this point is C. So over here, when the body touches the ground, potential energy, the formula for gravitational potential energy is mgh. H is the height from the ground. So here the height becomes 0 because the body has already come and touched the ground. So mg into 0, the potential energy is 0. Now, as the body comes down, kinetic energy keeps on increasing. And by the time the body reaches from its topmost to the bottommost point, the entire potential energy gets converted into kinetic energy, right? I'm talking about when the body just touches the ground. So here the kinetic energy becomes mgh because this potential energy at the highest point entirely gets converted into kinetic energy. So here also at the bottommost point, total mechanical energy is the sum of potential energy and kinetic energy. So 0 plus mgh, that also gives us mgh. Now this is the position of the body somewhere in between the initial point and the final point, right? So as you come down, the height keeps on decreasing and the speed or the velocity of the body keeps on increasing. That means as you come down, as the body starts descending down, potential energy keeps on decreasing, whereas kinetic energy keeps on increasing. Now this happens in such a way that at any point in between initial and final point, the overall sum of potential and kinetic energy, which is known as mechanical energy, remains equal to mgh. So at any intermediate point, the total mechanical energy remains mgh. This is known as the law of conservation of energy for a freely falling body only under the force of gravity without any external force. At the topmost point, kinetic energy is 0, potential energy is maximum, and by the time this body comes and touches the ground, the entire potential gets converted into kinetic, and since the height becomes 0, so potential energy becomes 0 and kinetic energy equal to mgh. And in between the initial and the final point, somewhere in between, maybe at 50% of the height, 75%, 60%, whatever be it, the potential energy keeps on decreasing and the kinetic energy keeps on increasing. Okay, but the overall sum of kinetic and potential, which is known as mechanical energy, remains constant, is equal to mgh. Hope this is clear to all of you. Now let's move on to a little graph. Let's see what is the pattern of the graph. So here we are plotting height above the ground along x-axis, and along y-axis we are plotting energy. Along x-axis we have plotted height above the ground, and along y-axis we have plotted energy. Now what did I tell you? As the body starts coming down, that means as the height decreases, potential energy also decreases. So potential energy is directly proportional with the height. That means as the body keeps on going up, its height increases, so potential energy also gradually increases. So this is the graph of potential energy versus height from the ground. And we know that as the body goes up, its speed decreases, and finally at the topmost point where the body is at rest initially, kinetic energy is 0. That means kinetic energy starts dropping. So as the height above the ground increases, because this is the topmost point, this is somewhere in between, and this is the initial point, here potential energy is maximum and kinetic energy is 0, whereas here potential energy is 0 and kinetic energy is maximum, right? So as we see that the height increases in this direction, so it reduces in this direction. So as the height reduces, kinetic energy keeps on increasing. See, as the height reduces, kinetic energy keeps on increasing. So this is the graph of kinetic energy. This one is for kinetic energy and this one is for potential energy, right? So as the height decreases, kinetic energy keeps on increasing, and at the maximum height, this one, kinetic energy falls to 0. Here is the diagram, right? And when the height is 0, that means when the body touches the ground, see, the potential energy is 0. Okay? So this is the graph, and this is the point, that means at this particular height from the ground, kinetic energy and potential energy are equal. At this particular point, kinetic and potential energy are equal to each other. Let's say if kinetic energy is 50 joule, then potential energy is also 50 joule at the point of intersection between these two lines. Okay. Now let us move on to the case of a simple pendulum. Let us move to the case of a simple pendulum. So this is the fixed support where the pendulum is suspended from. This is the bob of the pendulum. Now, when we take this bob either this way or this way, the bob has always a tendency to come back to its mean position. So here we will find out potential energy and kinetic energy. Now, this one is one extreme, this is another extreme. These two are the extremes, extreme positions. And this is known as the mean position. This is known as the mean position. Now let's see what happens. When a body is taken to this extreme, let us name the points A, B, C. Now when this bob is suspended, it rests at B. Now I take this bob to point A, right, and I release it. So what happens? This bob crosses this point. This crossing is known as overshooting this point B, and it moves on to C. That means as it crosses B and it goes towards C, its velocity keeps on decreasing, and finally when it reaches C, its velocity becomes 0. Because otherwise, if still some velocity would have been left, then the bob would have crossed this position as well, it would have gone here, but it stops here. That means velocity becomes 0, right? So at the extreme position, kinetic energy becomes 0. Now, this is at this much position, this much height from the ground. That means at the extreme position, the bob has certain height which it has acquired from the ground. So therefore, at the extreme position, potential energy becomes maximum. Same thing happens at this extreme also. That is, potential energy becomes maximum and kinetic energy becomes 0. Now why kinetic energy becomes 0? Because by the time this bob reaches either A or C, its velocity becomes 0. And the formula for kinetic energy is how much? What? Half mv square. So since V becomes 0, so at the two extreme, kinetic energy becomes 0. And at the two extremes, either A or C, the bob has gained maximum height from the ground. So gravitational potential energy becomes maximum. Now, when this bob crosses the mean position, then by the time it comes from B to C, as it approaches from B to C, its velocity keeps on increasing, and just when it reaches B, its velocity becomes maximum. And if velocity becomes maximum, then definitely kinetic energy will be maximum. So at the mean position, kinetic energy becomes maximum. And if we consider that the lowermost point of the bob just slides on the ground and move towards A, that means the bob is touching the ground. That means this height is becoming 0. So gravitational potential energy becomes 0. Gravitational potential energy becomes 0. Right? Now, just the moment when the bob crosses this point and goes towards A, again the restoring force, that means the force which wants to bring back the bob to its initial position, acts in this direction, B. Right? So the restoring force acts in this direction and the body has a tendency to go in this direction. That means force and displacement are acting opposite to each other, right? Now when force and displacement are acting opposite to each other, then the velocity of the bob keeps on decreasing, and finally when again it reaches A, its velocity becomes 0. So half m into 0 makes the kinetic energy of this bob at A as 0. And again it has gained h height from the ground. So its potential energy again becomes maximum. So if you are asked to draw this diagram, you will draw this diagram, you will mark these two extremes, you will mark the mean position, and you will write potential energy at the two extremes as maximum, don't specify any value, and potential energy at the mean position such that the bob is just touching the ground, potential energy is 0, and kinetic energy at the two extremes is 0, whereas kinetic energy while crossing the mean position, either going from A to C or from C to A, kinetic energy is maximum. Now, one additional information I would like to provide you is that everybody in this universe has a tendency to acquire the state of minimum potential energy. This is very, very true for each and everybody in this universe. Everybody wants to acquire the state of minimum potential energy. Now see, I'm giving you two examples. If a body is kept on top and it is released from a certain height, then definitely it will come under the force of gravity and it will have a tendency to lie on the ground, and when it comes down to the ground, its gravitational potential energy becomes 0, right? Similarly, over here, if you take the bob either to this extreme A or this extreme C and you release it, slowly it will start oscillating, it will go like this, and finally it will come to a rest. Now see, at the mean position potential energy is 0, right? So everybody in this universe has a tendency to be in the state of minimum potential energy, right? Whether it is the case of a free falling body, or it is the case of a pendulum, or it is the case of a spring, for everything this law is valid. And one more thing, potential energy always gets converted into kinetic energy. This is also very, very true potential energy always gets converted into kinetic energy, and then kinetic energy gets converted into different forms like heat, sound, light, whatever. But potential energy only gets converted into kinetic energy. Okay? Now, the last topic for today, that is work energy theorem. That means work energy theorem. Suppose here we have kept a body which is moving with initial velocity u. This body is moving in this direction with initial velocity u. So, initial kinetic energy of the body is, and the mass of this body is m. Okay, this body of mass m is moving with initial velocity u in this direction. So, initial kinetic energy is half mu square. Now, I have applied a force on this body in its direction of motion, right? Due to which its velocity will definitely increase because I have applied the force in the direction of motion. And suppose the velocity of this body now becomes v. So what is the final kinetic energy? That is half mv square, right? Now when you have applied force on this body and the body has been displaced in the direction of force, we say that some amount of work is done because the product of force and displacement is work. So whatever work we have done on this body, okay, that leads to change in kinetic energy of the body, and this is work energy theorem. Work done on a body is equal to its change in kinetic energy, and change is denoted by delta. Change is denoted by delta. So work done is equal to final kinetic energy minus initial kinetic energy. So work done final is how much? Half mv square minus half mu square. And if you take this half m common from both, then what do you get? V square minus u square. This is work energy theorem. This is work energy theorem. This expression in some of the books you will find this as the expression, and somewhere they have taken this half m common and written v square minus u square in a bracket. So whatever work we are doing on a body, that leads to change in kinetic energy of the body. This is work energy theorem. Okay, so here we end today's class and as well as this chapter of work power energy. So we will be back shortly with some different chapter, with some different new concepts. So till then, keep studying, subscribe to our channel, follow us on WhatsApp. Thank you, bye bye.